We know that chemical equations, when they're balanced, they represent a recipe, if you will, for a chemical reaction. It tells us the proportions in which our reactants combined to give us a certain amount of yield of product. So this concept of stoichiometry is simply using those mole ratios from the balance equation to calculate reactants consumed or the amount of products formed. In this video, we're going to take a look at a couple more stoichiometry examples and practice using that mole ratio from that balance equation. So here's example number 1. We're reacting 1.31 grams of magnesium solid and 50 milliliters of a 3 molar hydrochloric acid solution. And they react according to this balance equation below. That balance equation is the recipe. Use the coefficients as your mole ratio. We can see here that the coefficient of magnesium is 1 and the coefficient of the hydrochloric acid is 2. So if I know that for every 1 magnesium solid, 2 moles of hydrochloric acid are going to react with it. So they're always going to combine in that ratio. And they're always going to make 1 mole of hydrogen gas and 1 mole of magnesium chloride aqueous solution. So that's our recipe. For every 1 mole of magnesium, 2 moles of hydrochloric acid react with it. And they'll produce 1 mole of hydrogen gas and 1 mole of magnesium chloride. So down below here, you see a picture of this reaction. This coil, the silver coil, that's the magnesium solid. And we are placing it into this aqueous solution of the hydrochloric acid. And if you look real closely, you're going to see all of these bubbles in the solution. And a bubble is a gas trapped in a liquid. So that's going to be your gaseous hydrogen that's forming. Over here on the right, we're going to take a look at this chemical reaction in action and video form. All right, so here we have it. I'm going to pause for a little bit. Just want to point out the setup here. The students here have a piece of magnesium ribbon attached to this copper wire down here at the bottom of this tube. And all that copper wire is doing, it's holding our magnesium in place. And inside this tube is hydrochloric acid. And I'm just going to zoom in here and let you watch this reaction occur, and you're going to see that hydrogen gas being made. Okay, so all of these bubbles that are quickly being produced, they're bubbling up through the solution and they're collecting above the solution up here in this container. This method of collecting this gas in this big bucket of water is known as collecting gas over water. So we're essentially trapping all that hydrogen gas up here above our solution. But we'll rewind, let you watch that again. Okay, note your hydrogen gas being produced. All those bubbles, that's your hydrogen gas being made by mixing together the magnesium solid and the hydrochloric acid. Now returning back to our example problem, they want us here in part A to determine the limiting reactant and the theoretical yield in moles of the hydrogen gas. So remember that limiting reactant means the one reactant that is completely consumed. It's going to run out. And once it runs out, the reaction stops, and therefore it determines how much product is made. That theoretical yield is the quantity, the predicted quantity of product that is produced. And that prediction is based upon the mole ratios from our balance equation, aka stoichiometry. So I'm going to place the values of each one of my reactants below it in the balance equation, just to make this this word problem a little bit easier to understand. Let's just break it down before I try to solve. Let's just break it down into what we know. We know we're taking 1.31 grams of the magnesium and combining it with 50 milliliters of a 3 molar hydrochloric acid solution. Okay. Now, one of these is going to run out, but I don't know by just looking at these numbers which one it's going to be. Because they react in a given mole ratio, the first step is always to calculate the moles of each reactant. And so let's do that. Let's take our grams of magnesium solid and let's convert that over to moles. Okay, I've taken the grams of magnesium using its molar mass. We're going to get this value of moles for the magnesium, 0.0534979, and I'm truncating just a bit here, but I know I'm going to continue to use the value of my calculator. Now, all I've done is just converted our amount of magnesium available over to moles. Okay, and you can even copy down this value underneath of our balance equation. This equals 0.0534979 moles that we have of magnesium available for the reaction. Okay, let's move to reactant number 2, the hydrochloric acid. I want to calculate the moles of hydrochloric acid, but they didn't give me the grams. They gave me a volume and a molarity. You can calculate moles from that information. Anytime you have a solution and you have the molarity and you have the volume, molarity times liters equals moles. So remember that capital M for molarity, you can really think of it as moles of that solute, hydrochloric acid, over 1 liter of the solution. And if you think of it in that way, it helps you see that molarity times the liters is going to leave you with moles of the solution. So we are going to multiply this by 0.05 liters. And so again, this whole mole part over liters, that's your capital M. And so I'm going to multiply these numbers together to get the moles of hydrochloric acid. Okay, so we get a value of 0.15 moles of hydrochloric acid available. And so I'm just going to record that underneath of HCl in our balance equation. Okay, so I have the moles of each reactant, and we're trying to determine which one the limiting reactant is, and eventually the theoretical yield of that hydrogen gas in moles. And so this is where we kind of choose our own path in terms of solving this problem. Some of us are going to want to calculate the amount of hydrochloric acid needed for the reaction and compare it to the amount available. Some of us are going to solve for moles of hydrogen using magnesium first, and then repeat and solve for moles of hydrogen using the hydrochloric acid. So real quickly, I'll write out the 2 most common methods of solving this. And again, it doesn't matter which one you choose as long as you show the work and we're able to follow your work so that we can give you credit for your thought process. All right, here's method number 1. It's the compare required to available amount. So I've just taken the hydrochloric acid moles available, and I use stoichiometry and the coefficients, aka your mole ratio, to calculate the moles of magnesium required to react with the amount of hydrochloric acid. So I see here that 0.075 moles of magnesium would be required to react with all of the hydrochloric acid. And so now here comes the comparison. Compare this required magnesium to the amount of magnesium available that we have calculated above. And so what we're really doing is we're comparing this value, 0.075 required, to the value available, the magnesium. So you can see here how the amount of magnesium required is greater than the amount of magnesium available. So because we don't have enough magnesium, magnesium is the limiting reactant. Next step, if you choose this method, is to now take your available limiting amount and convert it over to moles of product. Okay, so we have already calculated the moles of magnesium available, so I'm just rewriting it here. And then I'm using my mole to mole ratio, aka your coefficients from the balance equation. It's a 1-to-1 ratio. And so the amount of hydrogen gas produced is 0.0535 moles, and then now it's appropriate to round for your significant figures. This predicted value, based upon the limiting reactant, is known as the theoretical yield. We predict that we will be able to make 0.0535 moles of hydrogen. Quick rewind before we move on to the next method. Small grammatical error here. Moles of magnesium required is greater than the moles of magnesium available. Sorry about that. Okay, method number 2 is called the, it's where you calculate the amount of product made by each reactant, and then you compare those two product quantities, and whichever one is the smaller quantity is going to be your theoretical yield. So here's what the work would look like. So typically students who choose this method, they're just going to take the given grams to them from the problem and just do all one-dimensional analysis grid here, as I've shown with the magnesium. So if magnesium was a limiting reactant and we used all 1.31 grams of it, the reaction would produce 0.0535 moles of hydrogen. Okay? Step 2, I would then need to take the given quantity of the hydrochloric acid and calculate the amount of hydrogen produced from that. And so again, the student would just take the known information about the hydrochloric acid. In this case, we know it's 3 molar, or in other words, 3 moles of hydrochloric acid for every 1 liter of solution. They multiply it by the liters of solution. And then they use the mole ratio to calculate the moles of product. So here I have calculated the moles of hydrogen twice. And now here's where the compare method comes into play. You are going to compare these two numbers. And the smaller number is the theoretical yield. And so our answer here is going to be 0.0535 as our theoretical yield. And that's the same answer that method 1 told us. Hypothetically, our stoichiometry predicts when we mix these quantities of reactants together, we're going to produce 0.0535 moles of hydrogen. Okay, so we always pick the smaller number if we are choosing this method. So down here, we can ignore that amount of hydrogen. We're not going to be able to make 0.075. Now, what is your limiting reactant? You identify that theoretical yield and you look back. What reactant made that amount of theoretical yield? That's this magnesium here. So the magnesium is your LR, your limiting reactant for this reaction, which we said the same thing in method number 1. We had identified the magnesium as our limiting reactant in method number 1. So here, it doesn't matter which method you guys choose. Whichever method you can do accurately and quickly. So we're going to go for accuracy first, whichever method you feel comfortable with, and you got to be able to do it relatively quickly. Okay, so you're either a method 1 or you're a method 2, whichever one you prefer, it doesn't matter. Now, a lot of times they want us to calculate the moles of product produced, like in this problem. But sometimes they want us to calculate the mass of product produced. No problem. We would just take our answer here of 0.0535 moles of hydrogen. Hey, multiply that by its molar mass, and you're going to get the mass of hydrogen produced. But other times, the problem wants us to solve for, let's say, molecules of hydrogen produced. No problemo. Just multiply it by Avogadro's number to get the molecules of hydrogen produced. So here's what I mean. In the previous part, we solved for moles of hydrogen produced. That theoretical yield is 0.0535 moles of hydrogen. But we can take it one more step. If they want me to calculate the molecules of hydrogen produced, I just multiply it by Avogadro's number, and we will have 3.22 times 10 to the 22nd molecules of hydrogen produced. Well, what if they wanted me to calculate the volume of the hydrogen gas produced? Like in part C here, they want me to calculate the volume of hydrogen gas that's produced. Well, if you know the moles of the hydrogen gas, and they're telling you here, oh, hey, here's the pressure of that hydrogen gas in atm, and here's the temperature, 25 degrees Celsius. What's the volume? Well, if you know that the moles of hydrogen produced is 0.0535 moles of H2, and that's a gas, and you know the pressure, and you know the temperature, and they're asking me to solve for volume. Okay, I've got V, P, T, and N all in one problem. What equation comes to mind? That's right, your ideal gas law, Pivnert. And so I plug and chug everything into this Pivnert equation, and I solve for the volume. Okay, I've plugged everything into the Pivnert equation, remembering that R is this 0.08206 liters times atmospheres, moles over Kelvin, and also that your temperature has to be in Kelvin. So I'm going to add 273, and that gives me a temperature of 298 Kelvin, which is what we're using in our Pivnert. Okay, and then let's just solve for volume. So volume equals 1.34. And now, final step, unit. Since the R has a unit of liters times atmospheres over moles in Kelvin, volume, when we use the ideal gas law, is in liters. And so here, I've just did stoichiometry and a gas law problem all in one. But the stoichiometry is simply using that mole to mole ratio to calculate the moles of the product. And then I just did a Pivnert problem using my moles from the stoichiometry answer to solve for the volume of this gas. So don't make it more complicated than what it is. Stoich is simply our mole ratio. And then after we do stoich, we can apply it to a gas law and solve for any of these unknown variables. Or, like we did in part C, after I do the stoichiometry part, I can calculate molecules or particles of our product form. So take-home message here, guys, is When we're trying to do stoichiometry problems, our first step is to always convert to moles of the given. Now, sometimes that given is going to be in grams, so we're going to need to use molar mass. Or sometimes it's going to be in particles, and we're going to have to use Avogadro's number, 6.02. Sometimes it's going to be molarity of a solution, so I got to do molarity times liters. And sometimes it's going to be the pressure of a gas, or they give me other variables of that gas, and I have to use it to solve for moles. And in that case, we're going to use PivNert. But all of these problems have the same thing in common. We're always trying to first convert to moles of that given. After we convert to moles of given, we're going to want to use the coefficients from the balance equations for our mole ratio. So insert mole ratio. This is the stoichiometry part of the equation. We're using those coefficients. After we have used our mole ratio, we'll now have the moles of our want. Okay, so we have moles of the want, and then sometimes they're going to ask us to take it a step farther than that. Instead of moles of a particular thing, they might want grams or particles or molarity or pressure. So it's the same thing, just kind of in the reverse order. Now we're going to go from moles to all these other variables that they could ask me to solve for. So I'm going to use what I have learned all along in chemistry. I can take moles and convert to all these different variables using all those tools in my toolkit so far. Alright, so let's apply this to one final example. Please hit pause, give you a chance to record the question and attempt the problem first on your own. Remember your roadmap. First want to convert to moles of the given, then I'm going to use stoichiometry, and then I'm going to convert to whatever unit they want me to solve for. Alright, so they've already told me what the excess reactant is. It's this sodium chlorite. That's your excess reactant. So we just know that we just got a lot of it and plenty of it for this reaction to occur. So that means the other reactant, the chlorine gas, is your limiting reactant. And that chlorine gas is going to determine how much product is made. What do we know about this chlorine? We know that it's a gas and it has a volume of 2 liters. It has a pressure of 1.50 atm and it has a temperature of 21 degrees Celsius. So I know the volume of the chlorine, I know the pressure of the chlorine gas, and I know the temperature. Okay, so remember in our roadmap, the first step is always to take that given and convert it to moles using whatever appropriate method applies. So in this case, I got volume, pressure, temperature of a gas. This is a PivNert problem. So it's a PV equals nRT. You are going to solve for N moles of this gas. Alright, so I have plugged in all the variables for the chlorine into PivNert. Remembering to convert our temperature into Kelvin here, adding 273. And I solve for N, and I get 0.1243 moles of chlorine gas. That is how much chlorine is available. And since I know that this is the limiting reactant, I just gotta now take this starting value of our limiting reactant and convert it over to grams of the ClO2. They're asking me to solve for the mass of ClO2. So if we're looking at our roadmap, we have just completed this step here. We've converted to moles of the given. Now it is time for this step, convert into moles of the want by using the mole ratio here. All right, so we are going to take our moles of chlorine and we are going to convert that to moles of our wanted product using stoichiometry and that balance equation. Okay, I've just done the stoich part. This is our mole ratio, 2 moles of ClO2 for every 1 mole of Cl2. And then for the last part, convert your want into whatever desired unit they're asking to solve for. We want to solve for grams, so we'll just do one more step here in our dimensional analysis and convert to grams. Okay, so we just multiply by the molar mass and we get an answer of 16.8 grams of ClO2 that will be produced.